How's it going, everyone? Mr. Geyser here with lesson 13B on trigonometry and polar coordinates. In this section, we'll show how to represent complex numbers in polar or trigonometric form. We first need to learn how to represent complex numbers graphically. Complex numbers are in that form of x is equal to a plus bi. Has two components, the real part, or a, and the imaginary part, b times I. We'll use the complex plane with two axes in order to graph the complex numbers on the real axis and the imaginary axis. To graph the complex numbers of a plus bi, we'll first use an ordered pair in those numbers of a comma b in this plane. In example 8 here, we want to sketch each point on the grid to the right, where in part A here, we're simply finding that it's equal to 3 plus 4i, where that 3 there is on our real axis, and the 4 is on our imaginary axis, where point A is just at 3 comma 4. Well, we're really just graphing this as if they were like an ordered pair. So for part B, we're going to go 0 on the real axis, and then up 2 on that imaginary axis. Well, for part C, we're just going to go negative 2 on the real axis and 3 on the imaginary. In D, we're going to go negative 4 on the real axis and then 0 on the imaginary, because we have a 0 there. We're skipping E. I don't like E. For F, we're going to go negative 1 on the real axis and then negative 2 on the imaginary axis. And notice that for G it's the same thing. We're going negative 1 in that imaginary because there's that imaginary or that invisible 1 coefficient in front of it. For plotting these points, we're just treating that real number as our x and that coefficient in front of our I as our y. We'll explore this a little further in this example 9, where in example 9, OP has a magnitude, a length, and a direction. The modules, or the absolute values, of the complex number z is equal to a plus bi is the absolute value of z is equal to the square root of a squared plus b squared. When we're taking this absolute value here, notice that we have this here as our hypotenuse. It is always positive because we're taking that absolute value. It's the length of this terminal ray here. For this theta amount, theta is being derived still from that inverse tangent of b over a here, where our a value has to be greater than 0, where our tangent value cannot be solved when it's negative. When it is greater or less than 0, we just need to add that pi there to it. But remember, we want to keep our a value as a positive value. Our theta is still the angle from that terminal ray here, where the a value is still in that real axis, and our b value is still in that imaginary axis. Now, as a side note, if a is negative, then theta is equal to inverse tangent of pi, or b over a plus pi here. Keeping that in mind. On our TI-84, the calculator is restricted on negative pi over 2 to positive pi over 2 for the inverse tangent of theta. Remember to adjust your answer to the quadrant where the complex number lies in based on the grid that we know it to be in. So if it's in quadrant 1, 2, 3, 4, based on that positive or negative a and that positive or negative b. In these next two examples, for example 10, we're going to find the absolute value of z and theta, and then graph z is equal to negative 5 plus 12i. Well, first thing, let's bring this information in where a is going to be equal to negative 5, b is equal to 12, and the absolute value of z is just the square root of that a squared plus that b squared. Plugging in that a and that b, negative 5 and 12, 5 squared is going to be 25, 12 squared is going to be 144. We add those bad boys together, get 169, and for those clever students, you guys know that's a perfect square to be 13. We now know that our z is going to be equal to 13, and we can write this trig triangle where our x is negative 5, our y is 12, and our hypotenuse is 13. But we still want to try and solve out what that theta is. So to use that, we're going to use our inverse tangent of b plus a. But remember, since a is negative, we're going to need to add a pi to this later on. So we take our inverse tangent of 12 over negative 5. We solve that out to eventually get this negative 1.176 radians from this value. Well, if we actually plotted that radian there, notice that since it's a negative value, we end up getting this terminal ray here. This is why we need to add a pi length. We're not finding this weird inside angle. We're actually finding the outside angle from this axis here. This is where we're adding pi, and this is why we need to add pi. We're in quadrant 2. Since we're in this quadrant 2, we're only solving for those inverse tangents in quadrant 4 and quadrant 1. We need to add that pi length to find the actual theta value for this point. Let's try this one more time for our example 11 here. We find that our actual theta is this just plus pi, 1.966. For example 11, we want to find the absolute value of z and its theta value where z is equal to negative 7i. Well, we can bring that information of a being 0 and b being that negative 7, where we eventually get that absolute value of z is still a squared plus b squared. Well, we plug in 0 for a and then negative 7 for b. We're really just squaring 7 and then square rooting 7 again to get 49, so we just get 7 as our z value. Well, this here is just going to create this line here. And we want to find that theta from that terminal ray, or for this terminal ray, from that 0 axis here. Well, if we plug in negative 7 or 0, we get an invalid input for our calculator. But notice, we can rationalize what this specific theta value is. Our calculator is going to give us an invalid domain error, but we can rationalize that this theta is actually 3 pi over 2 based on our understanding of the unit circle and by inspecting this graph here. Now, in example 13, we have that rectangular form of z is equal to a plus bi. We want to write this in terms of cosine and sine for polar forms. For this, we have this ABR trig triangle here where this inside angle is equal to theta. And notice that our cosine of theta for this is just going to be equal to a over r. So we can actually solve out that our a and our r here is going to give us a, or that a value here, is equal to our radius times our cosine theta still. And for our sine value for this theta here, it's going to be equal to b over r, where we know this is just going to be b is equal to our radius times our sine of theta. Beautiful. So our polar form in our imaginary or complex plane and our rectangular form going to that polar form have that same kind of formula here. Now, let's try and find the polar form equivalence of this z term here. Since we're plugging in a and b for r cosine of theta and r sine of theta, we can get these two equations. This here is the direct solve where we plug in these two values into this equation. This second one is just a little bit more simplified. We use this second form a bit more because it separates our r from both of these terms. So it helps us find r a bit easier if we use this second form occasionally. Now, a complex number of z equals a plus bi has a polar form or a trigonometric form, as z is equal to r times that cosine theta plus I sine of theta, where our r radius is equal to our absolute value of z, which is still equal to the square root of a squared plus b squared, and our tangent of theta is still equal to that b divided by a. The number r is the modulus of z, and theta is the argument of z. Now, in example 12, we're going to write the complex number of z equaling root 3 plus I in polar form. Let's bring that information here for a, b, r, and theta. where r, we're just going to square that a value and square that b value there. Eventually we get the square of root 3 is just going to be 3 plus 1, which gives us 4, and the square root of 4 is just going to give us 2. So we have that radius of 2. For our tangent, or for our theta, we take the inverse tangent of 1 over root 3, which really is just root 3 over 3. We simplify that out just a little bit. And eventually we get these two theta values. So we need to determine which one of these theta values here are going to give us the correct position for this point here. Well, we know we're going to be using that first theta because we're in quadrant 1 based off of our a and that b value. Well, now we can just plot this information here where our radius is 2, our b is 1, and our a is root 3. With this, we can now fill in the blank or fill in those positions for our polar form, and where our radius is equal to 2, our theta is equal to pi over 6, and our sine and cosine are in the correct position here. Let's try that one more time with example 13. For example 13, we're going to write the complex number of z is equal to root 6 minus I root 2 in polar form. Well, first, let's bring that information here, where our a is root 6, our b is negative root 2, where our r is just going to be the square of both of those, and our theta is just going to be the inverse tangent of that b over our a. When we solve out r here, notice that little pattern, where if we have both of these as root symbols here, and then we square them, they just magically go away. Make sure you guys feel confident that the square of a square root is just that inside argument. We eventually find that our radius is equal to the square root of 8, but we can simplify this out a little bit by saying it's 2 times the root of 2. For our theta value, we solve this out to eventually take out a root from that root 6 to get root 2 times root 3. This helps us simplify out that root on that top there, and now we have negative 1 over root 3, which we know is equal to negative root 3 over 3, which is just going to be 5 pi over 6 or 11 pi over 6. So we don't know which theta we're going to use yet. So looking at the graph based on our a and b, we know that the theta here is going to be inside this fourth quadrant, so we can get rid of that first theta because we're inside of quadrant 4. Now that we have all of our information on our trig triangle, we're just plugging all of this in to our z equation, where we know z now is equal to 2 root 2 times cosine of 11 pi over 6 plus I of sine 11 pi over 6. But notice a little bit of an extension here. What I mean to say is, instead of using this theta value, we theoretically could solve for this corresponding theta value here and get a similar looking equation that is perfectly equivalent to each other here. We could use this negative theta value here, and this might help us out in the future. Now, in example 14, we're going to change this polar form to rectangular form. Well, we know that polar form is just going to be equal to z is equal to a plus b times I. So if we're already in this kind of setup here, we actually know that our a value is going to be this cosine of 3 pi over 4, and our b value is this sine of 3 pi over 4. And we can find those values based off of our unit circle, where we know that cosine of 3 pi over 4 is equal to negative root 2 over 2, and sine of 3 pi over 4 is just equal to root 2 over 2. Well, now that we know what our a and b values are, we just have that 5 to take care of. Well, let's just distribute that 5 into both of those terms to get our rectangular form of z equals negative 5 root 2 over 2 plus 5 root 2 over 2I. Let's try that one more time with example 15. We want to write this complex number in standard form. Standard form is just another fancy way to write out as rectangular form, as a little reminder. For this here, we're given our a and b as that cosine and that sine there, where we find that cosine of 4 pi over 3 and sine of 4 pi over 3 is just negative 1/2 and negative root 3 over 2. We plug those bad boys back into the equation here, and then we just distribute 3 into both of those terms to get z is equal to negative 3 over 2 minus 3 root 3 over 2. Notice where the minus is coming from. It's just coming from that negative element for our y here. Finally, we want to take a look at the product and quotient of complex numbers. We're going to let z1 equal this equation here and z2 equal this similar looking equation here where we're changing the radius and changing the theta. If we were to multiply these two moduli here, we end up getting this radius times radius is times cosine of theta 1 plus theta 2. We already know those product of sums for cosine, plus I times sine of theta 1 plus theta 2. And we already know that product of sines, or product of sum of products for sines. Notice the quotient theorem, though, where we have our z divided by z is actually going to be our first radius divided by our second radius times our cosine theta minus theta 2 plus I times sine of theta minus theta 2 here. Let's explore this in our example 16 here, where we want to multiply and then leave our answer in that polar form. Well, first we're going to rewrite this so that we have all of our radius, all of our cosines and thetas here all set up. And now let's just plug these in. Notice that our radii are coming from this 2 and this 3, where we'll eventually do 2 times 3. For cosine, these thetas here are coming from this pi over 3 and this pi over 4, plus our I times sine of pi over 3 plus pi over 4. And then eventually we would use that product of sums for cosine and sine to solve out this equation here if needed. But for polar forms, we can just add these thetas together to get cosine of 7 pi over 12 and sine of 7 pi over 12. And our radii just multiply together to get 6. Try that about 2 more times here. Notice that for our rectangular form, we could eventually solve it out, but I don't want to. We're just going to use our calculators. We get this simplified rectangular form where that cosine of 7 pi over 12 times 6 would give us negative 1.553, and this sine of 7 pi over 12 times 6 would give us 5.800 times I. Now for example 17, we want to try and derive these two equations here, or we're going to divide these two equations and derive the polar form from it. We're going to use this setup here for that quotient, where our first radius is just going to be 2, our second radius is just going to be equal to 6, times our cosine of 9 pi over 16 minus 3 pi over 8, plus our I times sine of 9 pi over 16 minus 3 pi over 8. And then we would just subtract those theta values here to get this polar form. Now this is the unsimplified version. We would want to try and multiply out those cosines and sines, and eventually cosine of 3 pi over 6 divided by 3 or multiplied by 1/3 would give us 0.277. And for our y, we'd get sine of 3 pi over 16 times 1/3 or divided by 3. They're the same thing. Gives us 0.185. For our final example for this lesson here, for 18, we want to evaluate this expression with the knowledge that we can use this de Moivre's theorem. For this theorem here, we know that if x is equal to r times cosine theta plus I of sine of theta is a complex number and n, the square here, is a positive number, then we simply can find that our n is being squared to our radius, and then our n, the square from the original part, is being multiplied to our theta value. For example 18, we want to evaluate this equation here. We're going to go step by step where we have this original setup where the n value is going to be 4 in this case. Our radius value is just going to be equal to 2. So we bring in that 4 there. And then we bring in that cosine of 4 times that theta value of pi over 12 plus I times sine of that 4 times pi over 12. Simplify it out a little bit by multiplying out that 4. And eventually we could say that this is the polar, or this is the polar form here. However, we want to try and evaluate, this is in standard form. This is in standard form. For this here, we want to evaluate it just a little bit more here, or we can say that this cosine of 4 pi over 12 really is just 1/2, where remember, 4 pi over 12 is just pi over 3, where cosine of pi over 3 is just 1/2. Sine of pi over 3 is just root 3 over 2. And with that there, we can multiply in and distribute that 16 to get that solve of z is equal to 8 plus 8 root 3 I. Thank you very much for joining me in this lesson today. If you have any questions at all, please leave them in the comments down below. And I look forward to seeing all of you guys in class. Take care.